In this video, I'm going to illustrate how an asymmetric line shape can be used to fit data such as these titanium 2P. And the reason that I need an asymmetric line shape is that at least one of these doublet pairs derives from a conducting titanium carbide material. And I expect to see some form of asymmetry associated with this conducting material. I also have a doublet that corresponds to an oxide where I don't think the component peaks will be asymmetric. In fact, I think they're going to be symmetrical. The background that I'll use will be a Shirley background, and that's consistent with a conducting material. To construct a peak model, I need to create a background, and I also need to add components on top of that background that ultimately will fit the data. To do this operation, I'm going to use the quantification parameters dialog window. And I've selected the quantification parameters dialog window from a toolbar button that is on a new toolbar. The toolbar is aimed at creating options for the display state, in other words, how we see the data in the left-hand side. And while you can also invoke the quantification parameters dialog window from the options menu or from this toolbar button here, when I select from this new toolbar, I'm modifying the display state as well, and I'll illustrate what that display state looks like when the peak model has been added to the data. So the first thing I'll do is create a region, and the region allows me to specify an energy interval over which a background is defined. The default background has come in as a U3 2GAR background, which is suitable for a polymer. However, I believe this to be a conducting material, therefore I'm going to use a Shirley background. I'm also going to use an average width because I have a reasonable amount of noise in these data, and that will tie the intensity of the background to the intensity of the signal itself by averaging a number of data channels to take out the influence of noise. It's currently set as 1. I'm going to set this to 6 and press return. Now the action of the average width is to take a number of data bins either side of the vertical line, and the number is 6 in this case, so there will be 13 data channels used to average the signal in order to tie the background to the data. And if I want to make sure that this averaging is occurring, there's an option on the colors property page that says mark region average width. And when I do that, I see two vertical lines. And if I see two vertical lines both sides of this region, then I know I've got enough data to actually perform this calculation. So this is going to be the background. It's a Shirley background. The characteristic of a Shirley background is that the background responds immediately to a peak in the data. This Shirley S shape that we see here is very typical of metallic type background signal, and since this titanium carbide is a conducting material, we expect to see such a shape appear beneath the carbide peaks. The next step in creating a peak model is to go to the components property page on the quantification parameters dialog window. These are doublet peaks, so there ought to be for each photoemission line 2 peaks. If I press the create times 2, then I create 2 components. They are created in the proportions you would expect for a p orbital, that's 2 to 1. They've also come in with a 4/1/2 maximum constraint. This is just a default action. In this case, this default action is not appropriate. We'd expect the 1/2 peak to be wider than the 3/2 peak for titanium signal. So I've ended up with 2 component peaks that are currently very close in binding energy. In fact, they are quite far apart for titanium. And if I want to see these peaks more clearly, if I go back to my display toolbar button and press the create peak model button, then the way these components are displayed changes. Rather than being filled using the component color index, it's now just coloring using the standard colors for A, B, C, etc. and we can now see the outline of the peaks rather than the filled. And this helps to pick up a peak and move it to a new position. So I'm going to position these two peaks in this way because I believe that the offset between the titanium 2p 3/2 and the 1/2 is such that these two match, and that is consistent with these other two peaks matching corresponding to the oxide. So this is going to be the carbide and this is going to be the oxide. Since I intend these to be representative of the carbide, I'm going to change the name. So these two components both have the same name, and this is useful for the report spec where components with the same name, the intensity will be summed when I do a report spec using the custom report option. I would like to now create a pair of peaks that represent the oxide. Well, I could copy all of these, paste. I've got another pair of peaks here. These represent the oxide, but I will have to reposition the peaks to represent the oxide. So I'll first just change the name, and then if I hold the control key down and point at a peak maximum, I will move the appropriate peak for the oxide in both cases. So now I've got 4 peaks. The line shapes are all LA line shapes, and these are Voigt line shapes, predominantly Gaussian, quite a broad Gaussian relative to the Lorentzian. 0 would be all Gaussian, 100 would be all Lorentzian, so 20 is closer to the Gaussian. So this is not an asymmetric line shape and is probably inappropriate for these titanium carbide peaks. So when I say fit components, I produce a fit to the data which obviously is missing signal between the component that represents the 3/2 peak and the data. So what I need to do is modify the line shape to try and accommodate this signal that's missing. Otherwise I will underestimate the amount of carbide. I'm going to make use of a variation on the theme of a Doniach Sunjic line shape to model these data. I can enter a line shape that takes 3 parameters, and I've selected a DS line shape. The first parameter is the asymmetry. The larger the asymmetry parameter, the more asymmetry you'll see in the line shape. I've set it to 0.2. The next parameter is a width for a Gaussian that will be convoluted with the Doniach Sunjic line shape with the given asymmetry. And then the third parameter, in this case 40, represents a distance from the peak maximum which a Shirley background will be subtracted from the line shape itself. And that provides an asymmetry which is appropriate in some sense for use with a Shirley background that's calculated from data. If we didn't subtract off the Shirley background from the line shape, then that DS line shape would be infinite in area, and that's not very useful when we're trying to estimate intensity. We need a finite area in order to work out the amount of substance from this titanium that is bonded with carbon. So I'll press return to create this line shape, and you can see that the line shape has adjusted. The parameters have caused an extended asymmetry that goes on for quite a reasonable energy below the peak maximum. And I'd like this type of shape, not necessarily this one, but I'd like this type of shape to apply to both of these peaks that are associated with the titanium carbide. I could type in the same parameters in the line shape field in the second component, but one way I can systematically and quickly transfer line shapes between components on the components property page is to assign these two components the same component index, and then if I enter hash and then press return, it will update only the line shapes that have the same component index with the line shape that I've just indicated with the hash. Now you can see that the component index is different for these oxide peaks, therefore the line shape remains as an LA20. So now that I have two asymmetric line shapes, I will say fit. Now we have in this example a reasonable fit to this titanium 3/2 peak, but the fit is not so good elsewhere, and that's understandable. This asymmetry seems to project far too far away from the peak maxima for it to be physically meaningful. So let me reduce the extent of the asymmetry by changing the length, or rather the energy interval over which the asymmetry may go, and this is the point at which the Shirley background will be subtracted from the DS line shape. And when I set it to be 20, and I again in hash, both of the line shapes that have asymmetry for the titanium carbide are updated, and press a fit components button, and we start to get something that is a little bit more sensible. So let's make an adjustment here. Because the component property page is topmost, if I use the cursor I can point to the start of the background and just back off the background a little bit from the data and then attempt to fit again. And I've done that on the basis that I believe that these curves that represent the photoemission lines, they extend beyond the interval over which I have the background defined. I also think there are shapes in the background that probably extend in this direction too, so I don't expect the background to meet the data precisely. I can also make an adjustment to the other side, but I'll do that under the influence of the residual. So I'd like to look at the residual and point at the background at the other end and just make an adjustment so I can see the residual is more in line with the line shape that I've got and the data. Fit again, and we still have a residual that is shy on one side. We've certainly got a difference in the asymmetry in the data and the line shape for the titanium 2p 3/2. So let's increase the level of asymmetry and make this 0.24. So I'm increasing the amount of asymmetry. Let's say fit. And we're starting to move in the direction of a residual standard deviation that is closer to unity. That's what we would like to have. Not quite there yet, so I'm going to make a little tweak and say fit. And now I have a peak model where I can justify the line shapes on the basis of conductivity. I can also justify the number of peaks I've got in this peak model, and I'd like to think that with the use of relative sensitivity factors and transmission and escape depth corrections, that I ought to be able to compare the intensity of these peaks that I think are titanium bonded to carbon. They should be in the proportion of the material that I have in the sample. That should be 1:1 if everything is working out correctly. So at this point we should turn our attention to the carbon and see if we can identify a peak within the carbon envelope that corresponds to titanium bonded to carbon. We'll now develop a peak model for a carbon 1s that corresponds to the titanium 2p, for which the peak model has already been prepared. So if we display the carbon 1s, we see a range of peaks. And what's useful in this case is that one of these peaks is significantly different from what we would normally expect for carbon 1s. If we were looking at an sp2, sp3 type signal, then we might expect that to be a binding energy that's greater than 284.6. Graphitic carbon, for example, that would be somewhere around about 284.6, and every other polymer that I've worked with produces a carbon signal that is greater in binding energy than the graphitic peak. So the fact that we've got a peak that stands out on its own suggests that this is the carbide peak. So let's create a peak model, which once again will be performed making use of a Shirley background, and then add component peaks. So first of all, I'll just add in a set of peaks that are symmetrical peaks, all of these peaks. I'm just adjusting so that at least there is some sort of starting point for the fitting process. And if I say fit here, well, we get a fit that's clearly wrong. And it's wrong on two counts. You can see, despite having a reasonable residual standard deviation, we've got a very broad peak, we've got a very narrow peak, and the only peak that probably makes sense in any sense is this carbide peak. So let's recall the original set of components before pressing the fit, and I'm going to change the line shape for the one that I think is the carbide to a DS line shape. So I've got a relatively low amount of asymmetry, similar sort of Gaussian-Lorentzian convolution, similar sort of offset. And if I say fit, well, now I get a peak fit that really does look quite good. And the question is this an example of a peak model where I can identify carbide signal and pretty much ignore all the rest? So if I think this is my carbide carbon 1s, then the only role played by these other component peaks is to support the fitting of the data with this carbide peak. And what I'd like to do is compare the carbide peak from carbon 1s with the carbide peaks from the titanium 2p. So to do this, I need to make sure that I've got all of the names set up correctly. As to say, I want to have distinct names for components and regions, and I want distinct names for signal that comes from the carbide compared to these other carbon peaks. Now this is perhaps an assumption, but I'm going to make that assumption that all of these carbon peaks that are currently shown in orange, they don't count when I'm trying to do the comparison of carbide from titanium to carbide from carbon. So let's do the comparison now and see how well this set of peaks work out for us. Now I'm going to use the report spec and the custom report, and what I'd like to do is ratio the titanium that is bonded to carbon to the other components that I've applied to these data. And so what I did was I pressed the button ratio components, having selected the titanium 2p TIC component, and this has produced a names formula table that will allow me to create from the selected VAMAS blocks a quantification table that will show us how well these ratios are turning out given the peak models that I've just created. So let's have a look at this. So this is the result, where these are the ratio values of each of these different components, so all of the carbon other than the titanium, and then the carbon bonded to titanium, the oxide, and then the titanium bonded to carbon. That was the one I used as a reference, so that should be unity, and the one that I should look at is this carbon 1s, and it's 0.96. So that's about 4% in error, which is about as good as you ought to get from XPS. So at least we can say that the peak models that have been constructed using the DS line shapes are producing comparable results between the titanium and the carbon. It's entirely feasible that these peak models are not as well formed as they ought to be, but nevertheless, on the basis of the test that I just performed, there does seem to be some support for the two different peak models. Let's just display both of these peak models at the same time, and we will update the display so you can see that the signal in red corresponds to the signal in red between the titanium 2P and the carbon 1s.